Okay, so we talked about a CMG velocity steering law, where we solved d1 times gamma dot equal to this required torque that the system has to produce. And there's singularities. But we were kind of flying with one arm behind our back, right? Because we said, yeah, there's also these other motor torques, but we're giving a menial job of just keep the wheel speed constant. That's all that torque has to do. Because we are using US torques, those motor torques. As you spin, rotate, you will try to dump momentum in and out of those wheels, so the wheel speeds will vary naturally. So that torque has to be there. It's just doing a very basic job of holding the wheel speed constant. So what if we let it free? What if we let it do more than just hold a constant wheel speed? Then we can talk about the variable speed CMG, and let's see what happens to the math. So now I have this eta vector. So instead of gamma dot, or gamma and gamma like before, there was d1 times gamma dot, I have this new state vector, which is my wheel speeds and my gimbal angles. So now this Q matrix, which will be a 3 by 2n matrix, right? And the wheel speed torques that we produce were always about the spin axis, the classic thing. You're spinning here, you're torquing about this axis, you get the opposite torque onto the body, right? That was it. So I have the first n columns here are the spin axes of all the n VSCMGs, and the next n axes are all the transverse. Both spin and transverse all vary with time. So every time step, this is a new matrix, right? But now we can rewrite the problem and say, okay, if I have 4 VSCMGs, I have 8 knobs to tune. I have 8 motor torques I get to pick. And I'm not using 4 of them just to hold artificially a constant wheel speed. I say artificial. You don't want your wheel speeds to go to 0 because then you kind of lose all the CMG effects. But this math will let us actually drive them to 0 and drive them negative if we want to. We can do all kinds of crazy reconfigurations. And now this is the new control problem. Now without looking at the rest, do we still have singularity issues? Because I will have to do a minimum norm inverse of Q instead of D1. This is a 3 by 2n, so with 4 it would be a 3 by 8 matrix, and you take the minimum norm. Still have singularities? Henry, also nodding. Julian, do you agree? You guys know. If your wheel speeds are 0, then you would have issues, because you've lost the gyroscopics, then the accelerations go there. So if we have non-zero wheel speeds, do we still have a singularity? Well, look at what happened with the GTs before, right? If you were here, the 2 gimbals are pointing kind of in a pyramid configurations, but the other 2 can rotate, and if all your GT axes are lined up in a plane, are your GS axes, are they going to line up in the same plane? Is that possible? No, it's impossible, right? Because they have to be orthogonal to the GTs. Now you could line them up if you put all your gimbal axes vertically, yes. But then you're kind of hosed to begin with, right? Because you never generate a 3-dimensional stuff. That's why we have a pyramid configuration. So don't put your gimbals like this. You kind of want to tilt them. So, but then when these things line up, the other ones have to poke in and out of the plane, right? Up or down. And so the GSs, there's no way that they would go. And vice versa. If you have a GS configuration that all goes coplanar, the GTs will be out of plane and spanning all kinds of space there. So, so the classic CMG singularity that we had, where all the GTs line up in a plane, still happens, but this matrix retains full rank. Which means now all of a sudden, I no longer have to keep pointing at Boulder and swerve and look at Denver and then back to Boulder again as I'm flying over it, because I hit a singularity condition. But I'll be able to come up with ways, but I have to modify my wheel speeds. And all of a sudden, I might be going 500 RPM faster or slower, and then what do we do with all of that? That's kind of what we want to investigate. You see that? So yes, but if the wheel speeds go to 0, then you could, because then these terms will basically become zeros if all the wheel speeds go to zero, and that could be a singularity. So the zero crossing is a separate thing. And that might be an interesting project just to study that. How can you reconfigure, change speeds? How drastically can you dump momentum back and forth if you're interested in that? So here's the minimum norm inverse that we're going to do, like before, but we don't have to do a plus alpha times I or anything like that. Now here, it's going to find the minimum norm of wheel speeds and angles. What units do wheel speeds have? Radians per second, not a trick question. Angles, radians. So we're mixing units actually here. And that's a little bit tricky, like minimum norm. If it's just angles, I'm going to get the least angles, or the least angle rates. That's easy. But you've got a little bit of apples and oranges in here, and we're finding mathematically the minimum norm of that. And that's not necessarily the best, all right? But this is what we've done. The original stuff was doing this because, in the end, I don't want to use the reaction wheels because I know they're much less efficient. I get way more bang for the buck if I use the CMG modes. So we will look at modifications to this such that I force it to use the CMG mode as much as possible. But if I get near these gimbal lock situations, I can smoothly bring in the reaction wheel mode, drive through it, and then resume with the CMG again, you know. And that was the original paper I wrote on this topic. The kind of brute force gets you through there, you never hit singularities, but it comes at a cost. We all of a sudden have to use reaction wheels to get this third torque component. And it can cause drastic changes, and we'll see what happens to the power. And there'll be other things we can do that worked out to be a little bit more practical. But this is the basic idea. So you can do, when you do a minimum norm inverse, you can also do a weighted minimum norm inverse, that you're giving everything weights. And always, these weights, the numbers are arbitrary. It's the relative, the absolute values are arbitrary. It's the relative size that's important. So typically people just use all ones if they're all equally weighted. But if you make the CMGs ones, you might make the reaction wheels 0. That would force the reaction wheels not to be used in this case, right? You would basically impose 0 wheel speed changes if you made the weights 0. If you allow for a little bit of reaction wheels to be used, you would have a non-zero value, and vice versa, right? So that's cool. What we typically do then is I have constants for the gimbals, because I want it always nominally to be working, and I would pick something like 1. But I get these knobs that I can tune that says, okay, sometimes I want to use reaction wheel modes, but other times I don't. And when do you or don't you want to use reaction wheel modes? It all depends on the condition number of this D. And here I have D, not D1, because I'm doing the full tracking problem. So depending on tracking or regulation, you'd have to put in the right D in there, you know, with all the terms that it entailed. So how do we measure if this thing is full rank? What options do we have? What do you think, Disip? Sorry, convert it to what? Okay, row echelon form. How does that tell you if it's singular?
Just measure the rank using row echelon.
Okay. Might work. I haven't tried that approach. Sounds a little bit more complicated. I just need a measure. I need a metric that says I'm close or I'm not close to a singularity. Determinant, definitely. Besides determinant, what else? Condition number. Anybody not know what a condition number is? Okay, 2 people. So Julian, you didn't raise your hand. What's a condition number? See, you should have raised your hand, man. I love asking the question that way, because that way I can pick on everybody who just sits there and doesn't pay attention.
The smallest eigenvalue divided by the largest one?
Opposite. The largest, not eigenvalue, but singular value.
Yeah.
So we also can look at singular value decompositions. So if you don't do a wiki quickly, if you haven't done with those, it's like an eigenvalue, eigenvector. It's very related. In fact, singular values tend to be, I believe, the square root of the eigenvalue or something like that. But it's the largest singular value of the system over the smallest. Because if you're singular, what happens to your smallest singular value? It goes to 0. That means your condition number goes huge, and that's bad. If things are really well behaved, what should your condition number be? 1, right? So if everything's like unit 1, 1, 1, everything, but everything is 10, 10, 10, they're all about the same order. You've seen in MATLAB when it goes yelling and crying at you that, hey, you're doing a matrix inverse that's ill-conditioned, right? You have a huge ratio. There's a million, there's a billion, and there's 0.00002. It's not 0, but there's such a huge discrepancy with 16 digits of math even. It knows it's losing some arithmetic accuracy by trying to attempt this inverse. So with the singular value decomposition, go take a look at that one if you haven't. It's really elegant. Then that's how we basically can do a minimum norms, least squares, all of this. And if you're at a singularity, you know, once you have, like with an eigenvector, eigenvalues, you can, given the eigenvector, eigenvalues, you can, you know, put the eigenvalues in the middle, pre and post multiplied with matrix of eigenvectors, one of them transposed, and you reconstruct the matrix. If you do the inverse, you do the same thing. You just do 1 over the eigenvalues. The same thing with singular values. But instead of doing 1 over 0, or nearly 0, because that thing's going to be huge, right? What do we do with the singular value then? Or the nearly singular value with an SVD inverse? Anybody know?
Set it to 1?
Not to 1.
The lowest non-singular number?
Almost, if you have singular values there. So if you have this matrix of singular value 1, 2, and 3, and then we're doing the inverse, typically you would have 1 over singular, you know, that one, 2, 3. But if sigma 3 is the smallest one, and that's gone to almost 0, or is 0, this is the problem, right? The trick is you simply set it to 0. And then you carry out, you have your left and right eigenvectors that come out of the singular value decomposition, the u and v that happen there. You pre and post multiply, do this, and you get the inverse of the matrix, but you get the inverse, like a minimum norm one, without the singularity. So that makes it a much more robust way that you get the best projection on all the comparison. So the paper by Kevin Ford and Chris Hall was using this SVD inverse in particular to figure out, well, I'm going to do that. And then I get the parts that I can do perfectly. I don't mess with them. I just have to zero this part of the response that I can't do and let it drive through that instead. Okay? So there's different measures of doing a singularity of a matrix. And we can look at a variety. You had a question?
Yeah. So going back to the situation where we just have CMGs.
Yes. Okay.
The SVD decomposition, the inverse, that would project that torque into.
Exactly. So the question was, if you do go back to the CMG case, like I can just go here, right? If we go to the CMG case here, instead of doing this modification, which just kind of nudges it around and, you know, fudges it, this one, if we did an SVD essentially, it will then give you the torque in the plane that you can without nudging and fudging, and the one you can't, it just zeros in the end automatically by doing an SVD inverse. Yeah. So again, you will have path deviations because we're not getting the full control torque, but it won't mess with the two components you don't. So you can kind of trade off which one gives you more desirable behavior. So with ours though, we're not going to have a singularity, but we want to take a measure of the CMG singularity. And when we are almost singular, that's where we want to bring in the reaction wheel modes, let them be included, and then when we're away from the singularity, turn them off, and our wheel speeds should resume to go to 0, because then with 0 weights on this, we will end up with answers that just says, okay, those are all going to be 0, that you get out of this weighted minimum norm inverse. So one of them we can do is you can have these weights minus mu times delta. Delta is some singularity measure like the determinant. So if it's 0, this will give you 1, but if it's non-zero, it would give you something that would, you know, decay very quickly. And with mu, you can control how sharply, this is like a Gauss bell curve, you know, that you would have. You could also throw in the singularity index. So here I'm using the determinant, and just for well conditioning, I'm dividing by the nominal momentum that the wheels had. There's D1 has a huge momentum term in it. It just made for really large numbers and dividing by the nominal one. I don't care about the magnitudes, I care about the directions of these things. So it gave me better conditioning to get this determinant done. So that's, in my original work, that's what I used. I used a determinant, but you could have used other singularity measures and doing this. So this now gives us a steering law that'll tell us this is the wheel acceleration, this is the gimbal rates that you need, and we will always produce that required torque. And things work from there. No singularity. But again, it comes at a cost. We have to now, you may have, if things were moving quickly because your control expected you to be agile, and all of a sudden the reaction wheels have to take over 1/3 of the control, they better be strong reaction wheels, right? If all they have to do is maintain a constant speed, they can be much wimpier reaction wheels that you put on there. So that becomes a challenge to look at. But as far as research goes, this is actually an interesting question too, is because here we have different units, and is there a way to rewrite this? In the end, we care about motor torques. Could you, but this is gimbal rates, not motor torques, so we'd have to do some interesting massaging. But it would be nice that we don't have an apples and orange minimum norm that I have to artificially put in weights with a mu function that I'm kind of hand tuning to get it to perform well. Could you just let the system figure out which torques, or do you base it on energy, or how do you do this there's an infinity of ways this could be done, actually. This might be interesting research projects. Throwing out some ideas.